Welcome to the afternoon session. Now, as a reminder, there's only one speaker this afternoon, so we'll have all the afternoon for discussions and non-talk activity. Okay, so this afternoon we have Davide Masoero from Lisbon, and I'll let Davide tell us what he's going to talk about.
Thank you very much for the presentation and for the invitation. It is my first time in Cambridge. I'm very happy to be here. And I like a lot the snow too. I'm not used to it. So my talk will be about Bethe Equations and spectral determinants. Now, last time I gave this talk, a person in the audience complained about the use of the word Ansatz, so I will drop the word Ansatz in my talk. So it will be Bethe Equation and spectral determinants. Solutions of Bethe Equation and spectral determinants. So the talk is based on 3 recent papers with Riccardo Conti and with Andrea Raimondo. The last one is still in the archive, and the other 2 were already published. And some ongoing work with Gabriele Degano, who is a PhD student, Yevgeny Mukin, and Andrea Raimondo again. So I was asked to give a big picture, but I'm not very good in big picture because I like details more than big picture, but I'm trying. So this is my vague big picture. So the big picture is the following. It is a general fact that most interesting problems in mathematical physics can be expressed via the monodromy data, or generalized monodromy data, of a linear ODE in the complex plane. Okay, it is maybe even a definition of mathematical physics for me. So this was since Gauss and Riemann were working a lot on linear ODEs with regular singularities. And then there was this work of Stokes and many other on irregular singularities. And what we have noticed in the last 40 years, maybe, is that quantum field theories and related geometric objects often correspond to equations with irregular singularities. And then, so the second part of the vague big picture is these things that I call nonlinear Stokes phenomenon, which is a word that is used often, sometimes in the Bethe equation literature. What it is about. So when you have an irregular singularities, as we all know, the solutions have some asymptotics in some sector, and then they change asymptotics when you cross the sector, and you call this the Stokes phenomenon. And then, and now you consider, well, instead of the solution of the linear ODE as their object, you consider the monodromy data of the ODE, like the Stokes multiplier, as a function of h bar. And you consider the asymptotics in sector of the h bar plane. And you would notice that they have some asymptotic in some sector, and then when you cross the sector, you have another asymptotic. Okay, it is what you would call sometimes wall crossing formula. Okay, it is a quite general phenomenon. And this wall crossing formula, or nonlinear Stokes phenomenon, is observed in integrable quantum field theory and related geometrical objects. For example, in the theory of Dubrovin-Frobenius manifold, WVV equation, and Gromov-Witten invariant. And this very famous series of work by Gayotto, Moore, and Naitsky about BPS spectrum, DT invariants. Possibly Andrew Naitsky will talk about this in 2 days. And another example, which is the example I'm talking about, is this ODE IM correspondence.
Sorry, what's IM?
IM?
Yeah.
Well, integrable model.
And DT?
I'm sorry, this is Donaldson-Thomas. BPS, I cannot, it's too complicated for me to say. Okay, so let's start with something in principle simple, but it becomes complicated. So I just consider this family of anharmonic oscillators. So you have a monomial potential with an exponent which is in general a real number, a real positive. But for the sake of today's talk, to avoid some technicalities, I will just consider when this exponent is greater than 2. And then you have like this angular momentum term, which in principle is complex. But again, for the purpose of today's talk, is just a positive number. And then you try to solve this Schrödinger equation, and you look for the energy level of this eigenvalue problem. You are looking for solution which decays at infinity and at 0. And then you see that the spectrum is discrete, simple, and positive. And you call the spectrum the point in the spectrum the nth energy level, depends on the momentum. When n is an integer number, for me 0 belongs to the integers, and it has these asymptotics. Okay. You see here well, you see the momentum appear here explicitly as kind of shifting the quantum numbers. And the spectral determinant as a function of the energy is an entire function of order 1 plus alpha over 2 alpha.
Basically, for L equals 0, I suppose you could allow psi of 0 to be finite.
Well, yeah, I mean, I can define for every value of L.
No, but for L equals 0 is special.
And L is equal to 0?
Yeah.
Well, yeah, I mean, you have Dirichlet and Neumann. But you have the same kind of Dirichlet and Neumann for every value of the complex, for every complex value of L. Okay, so in our case, when alpha is greater than 1, the entire function has order less than 1. It means that you can factorize it very simply. Okay, it's kind of as a big polynomial, let's say. Okay, and the starting point of my talk is this discovery by Patrick Dorey and Roberto Tateo, which is the following fact, that the spectral determinant of these anharmonic oscillators satisfies a countable collection of identities, which we can think of as exact quantization condition. And the identity is this one, so you have e to the minus 4 pi I p, where p is like a quantum field theory momentum, which is given through this formula. And then you take the spectral determinant, you rotate it in one direction, you rotate it in the other direction, and you divide, and you get -1 for every point in the spectrum. Okay, so this is not an identity. So for every point in the spectrum, for every energy level, we have this kind of identity. So they're very nice. So these identities are very beautiful for this. Well, they are beautiful in itself, and they're beautiful because these are exactly the Bethe equations of an integrable quantum field theory, which is called a Quantum KdV model. Okay, which is also a conformal field theory with central charge less than 1, and it is the conformal limit of the 6-vertex model, where the anisotropy delta is between -1 and 1, for those who know this 6-vertex model. Okay, so now we have this equation. I mean, we have a solution to this Bethe equation. So, but which solution? Because this is a quantum field theory, so it has many states. And Patrick and Roberto say, well, this is the ground state of the model. Okay, so let me skip a bit. So we have, I want to present this like diagram, which is the ODM conjecture for Quantum KdV model. So on the left, here we have the Bethe states of Quantum KdV. So these were introduced by Bazhanov, Lukyanov, and Zamolodhchikov in the physical literature. Still, there is still no proof in the mathematical literature that they actually exist. But for sure, they do exist, but I mean, the mathematical theory is a bit incomplete in this case. Okay, and then we should find a correspondence to every Bethe state of quantum KdV. We should be able to associate an anharmonic oscillator. Okay, so I will call them monster potential in a few slides. And so what is the relation is that you take a Bethe state, you take a solution of the Bethe equation, and then you take the spectral determinant of the corresponding anharmonic oscillator, and they should coincide. But we still don't know whether these exist, okay, mathematically, but we know a lot of properties of this object. So for example, the Fock space is a graded vector space. Okay, so there is like, so the Fock space, which would be F delta C, it's graded. And we know the dimension of every component.
It's kind of hard to see the red.
Oh, I'm sorry, yes. White, you're right. So where is, so I'm going here. So we have this Fock space, let's say, of the model. Maybe we'll call this big N. And we know the dimension of every component, which is exactly the dimension of the nth component is exactly the number of integer partition of n. Okay, so for example, we know that also we should be able to define a grade somehow here and find like partition of n monster potential of degree n, whatever it means, the degree in that case. And also here at the level of Bethe equations. So the Bethe equation, they exist in itself, in themselves, I mean, they are equations. So we should be able to define like a topological invariant, like a degree, and fixing this degree, we should be able to find partition of n solution of the Bethe equation. Okay, so there is this object infinite dimensional, but it is graded in finite dimensional parts. And this should simplify our life. And we should be able to find this partition of n in all these three boxes. So, and the solution of the Bethe equation we are considering, because you can have the same Bethe equation for different models. The analytic properties of the solution would tell you which model you are considering. So in our case, we are considering solution of the Bethe equation whose zeros are almost all real and positive. Okay, so this is our analytic setting. Now, the problem is to classify a solution of the Bethe equation. Okay, but there is a long physics literature about that. In particular, there is an old paper by Yang in '63, which tells us what more or less we should do. So what is solution? The problem is classify solution of the Bethe equation such that almost all zeros are real and positive. And for today's talk, I just simplify the problem, and I assume that all zeros are real and positive. And moreover, I assume that the asymptotics of the distribution of the zero is the same as the asymptotic of the distribution of the spectrum of the anharmonic oscillator. And so what is the solutions to this problem is that, so the Bethe equation are exact quantization condition, but they do not tell us which states are occupied or not. So it's an information that we have to put in the system in order to find a unique solution. So we have to add information on which quantum numbers are occupied and which are vacant. So, so you see, now we consider this quantization condition, and we look for all solution of this quantization condition. And we say that, and we call this sequence EK. And we say that K is a root number if the solution of the quantization condition corresponds to a zero of the spectral determinant. Because Bethe equation tells us that if Ek is a zero of the spectral determinant of the Q function, then this quantization condition is satisfied. But the converse need not to be true. Okay, so we have like define a sequence of root numbers. Okay, this sequence Kn, with n is an integer. So we have this increasing sequence of root numbers. Yes?
You are not assuming that the asymptotics of the Q function coincides with the asymptotics of the known spectral determinant.
Yeah, I do assume that. I do assume that.
Then I think all the roots are occupied.
No, there are like, there is a lot of, there's still a lot of freedom. Okay, because I assume that the energy,
Because when I worked on this problem, I thought about that.
Yeah.
But I argued that if there are more zeros of this equation than eigenvalues, then the Q function asymptotics will not coincide with the Weil theorem.
well, I don't know. I don't know exactly what you mean, but but we have this sequence of root numbers and also a finite sequence of alls. Okay, now there is like ambiguities. This is very technical. There are two ambiguities. One is the numbering, because if I add, so when I count the quantum numbers, I start from an integer which is arbitrary. And also, you see the phase P. Also, the phase P is there is an ambiguity, because if you add a half integer, then you get the same equation. But there is a natural way to fix these ambiguities. Well, the important one is that the sequence of root numbers eventually stabilize. Okay, so K of n is equal to n for n large enough. And then there is another technical way of fixing the phase of momentum ambiguity. Okay, but now we are given, we are supposed to be given a sequence that stabilizes, an integer sequence which is bounded and stabilizes. And this we know, these are classified by partition of integer. Okay, like if you take the sequence 0, 1, 2, 3, 4, 5, which would correspond to the ground state and also correspond to the empty partition. Okay, and then you go to the partition of 1, and you would have the sequence minus 1, 1, 2, 3, which means that you have an all, you have inserted an all here at 0. Okay, so in the theory of integrable systems, sometimes this picture is called the Maya diagram. To every partition, you associate a Maya diagram, and it is something like this. Okay, for me, dots, black dots are roots, occupied quantum numbers, and white dots are alls. Okay, and now we come to this conjecture by Bazhanov, Lukyanov, and Zamolodhchikov, which we're working on Dorey and Tateo, the IM correspondence. And they knew how solution should look like. And they say, fix n, an integer, and assume that the moment is greater than n plus 1/2. Now, for every partition, lambda of n, the Bethe equation admits a unique, up to normalization, solution whose sequence of root numbers coincide with the sequence associated to the partition. So, okay, again, so we choose a partition we get a sequence of root numbers, and we look for a unique solution of the Bethe equation with this given sequence of root numbers. And they claim that it exists always whenever this inequality is satisfied. So whenever the momentum is large enough. Because when the momentum is not large enough, then some roots will go to 0, and then they become complex. And second part of the conjecture is that any of such solution coincide with the spectral determinant of a certain anharmonic oscillator. Okay, so what Dorey and Tateo gave us is like the ground state. The ground state anharmonic oscillator. And then they say, well, but there is an anharmonic oscillator for every state. So first, I analyze this part of the claim, and then the second part of the claim. So, this is in the more recent paper with Riccardo Conti. And so we did asymptotic analysis of this Bethe equation when the momentum is very large and positive. Okay, so we fix an alpha must be greater than 1 for our result. Okay, it depends technically on this fact that the order of the spectral determinant is less than 1. So we fix an alpha, which is, let's say, the degree of the potential at infinity. We fix an integer and the repartition of that integer. And if P, the momentum, is sufficiently large, we prove that the Bethe equation admits a unique solution, Q lambda P. Q is a function of E, and depends on two parameters. One is the partition and the other the momentum. So the Bethe equation admits a unique solution whose sequence of root numbers coincide with the sequence associated to that partition. Okay, and also we prove a quite strong uniform asymptotic of the roots all for that given solution. But I will not show it because it's a bit, I should introduce more notation that I would need. So what about, but our paper does not come out of blue, but there were a lot of, in the physics literature, there were a lot of results. In the mathematical literature, not so much. So about well-posedness, for alpha greater than 1, for this fixed value of the momentum, and for lambda to be the empty partition, R2W proved essentially our result. He had another approach because his approach comes from André Voros, but it is essentially equivalent. Then there is another approach based on the thermodynamic Bethe Ansatz equation, where again you must be in the empty partition case for the ground state, and alpha must be, the potential must be integer. And this more recent paper by Hilfiger and Runke. Now, in the physics literature, there were a lot of results. Well, Bazhanov, Lukyanov, Zamolodhchikov, they already knew the result. Okay? They didn't care about proving it, but they already knew the result. Then there is also this paper by Fioravanti and Rossi that does similar analysis. Of course, there is the paper by Destre de Vega, where they introduce the technical tool which I'm going to analyze next, which allow us to prove the theorem. But essentially, the idea of roots and alls goes back to Yang and Yang paper in '66. And the kernel, I will write an integral equation, and the kernel was already written in '38 by Hulten. Even though I couldn't find the paper because it's in a Swedish journal, I couldn't read it, but it is claimed in the literature that the kernel that I'm going to show was already in this paper by Hulten. Okay, so what is the idea beyond the proof is this thing which is called Destre de Vega equation. So I take the logarithm of the Bethe equation, which is the thing that physics always does when they analyze Bethe equation. And I introduce what in physics is called counting function, even though in mathematics it should not be called counting function, because this is like a real analytic function, while in mathematics counting function is discontinuous. So, but it's just like the left-hand side of the Bethe equation. the logarithm, you take the logarithm of the Bethe equation. The left-hand side, you call it the counting function, z of e. Now, so on the right, you have the logarithm of -1, okay? And so the Bethe equation, together with the information on which roots are occupied, becomes this logarithmic Bethe equation, which are kind of, I will show you why, exactified WKB equation, because so if you here, instead of having an unknown function, you would have like a WKB integral, this would be like the WKB equation. Now you take this system of transcendental equation and you transform it into a single free boundary nonlinear integral equation. Okay, free boundary, it's called free boundary because you are integrating on an interval, and the endpoint of the interval is an unknown. That's why it's called the free boundary. And this equation is called Destri-de-Vega equation in the literature. And what I do then, I do asymptotic analysis because it's the thing that I know how to do. So I linearize this equation in the large momentum limit, and I do some perturbation analysis to show that there exists a unique solution. Now, this is very technical, but I'll show you for reference. Maybe in the future you will need it. So, and I want to show this Destri-de-Vega equation. So first of all, you have to fix a partition, and then you call big H the number of holes greater than the lowest root. Okay. Like, for example, for the ground state, big H is equal to 0. There are holes, but they are all on the left of the lowest root. And now when you have fixed lambda and you have this big H, then the unknown of the Destri-de-Vega equation is not just an real analytic function, but an n-tuple, where omega is the left endpoint of the integration interval. Then these small h1, small h, big H are the position of the holes which are greater than the lowest root. And finally, z, which is our counting function, which we assume to be where we look for it to be differentiable, strictly monotone, and there's this, to have this asymptotic at infinity, which is the same asymptotic that you would get from the spectral determinant of the anharmonic oscillator. Well, and the Destri-de-Vega equation is this system. Okay, so you have here a nonlinear integral equation. It is nonlinear because the kernel is integrated against the ceiling function of the counting function. So this is very nonlinear. So the ceiling of z minus 1/2 is what in physics should be called like integrated density of state. Okay, so supposing we were in the ground state, we just would have this term, but then for higher state we have like a forcing term. Then the second equation is the equation for the endpoint of the integration interval. And it is just the fact that the ceiling of z of evaluated at the endpoint minus 1/2 should be equal to minus big H. So you see, it is a free boundary problem, but it is like piecewise constant, this function, so it's not, well, it has some difficulties, but I mean, it is almost look like a standard, not free boundary integral equation. And then finally, you have some condition about the holes. Now, what I normally do is like I try to do asymptotic analysis, and so we linearize the problem. Okay, something which was already done in the literature. So linearizing means that instead of taking the ceiling of z minus 1/2, you just take z. Okay, you substitute this strange function with just z. And so we have this linear integral equation. Okay, this is like it is a Wiener-Hopf equation, and in the literature, you could find solution written in terms of like inverse Laplace transform of subproduct of a gamma function. And this is like a very bad representation, because we need to have z. We need to prove that it is like positive, it is monotone, etc. But from this representation, it is really messy. But what we did, we discovered that the same formula, it is actually a WKB integral. Okay, so we don't have any direct way from passing from that formula to the other formula, but just they solve the same linear equation, I mean the same integral equation, and that equation has a unique solution. But this equation is very important because it is, let's say, an hint of the ODM correspondence already. Because right now we are just considering Bethe equation. We don't know anything about spectral determinants or anharmonic oscillator. But when we linearize the Dirichlet equation, we linearize the Bethe equation, we see that we can express the solution of the linearized equation in terms of WKB integral. Okay, so this is like exactly the WKB integral of the Dorey and Tateo anharmonic oscillator. And that's why I called the Bethe equation the exactified WKB, because if you put in the Bethe equation here the linearization, then you would get the standard WKB quantization condition for the anharmonic oscillator. Okay, but the Dirichlet equation gives you the full expansion. I mean, instead of giving you just the WKB approximation, they give you the exact counting function. Okay, now I don't think I want to do that, but simply I want to say that the analysis is quite challenging because so you need to show that there is some contractivity, but these integrals are bad, and but somehow we were able to prove contractiveness of this map, at least for large P, because so the factor here that you need to be less than 1, it's 1 over P, okay, times a constant. Okay, so when P is large, the map is contractive, and then we could prove the existence as unique of a solution. Okay, now let me go to the second part. So here you remember or not. So this ODM conjecture was existence and uniqueness of a unique solution of the Bethe equation with given root numbers. And the second part was every such solution coincide with the spectral determinant of some anharmonic oscillator. So this is again Bazhanov, Lukyanov, and Zamolodhchikov guessed the result. Okay, and they were correct. So, and they call it monstrous potential or monster potential. So suppose R is a monic polynomial of degree big N, and you consider the spectral determinant of this potential, which is like the ground state potential minus twice the second logarithmic derivative of R evaluated at x to the 2 alpha plus 2. Okay, this looks a bit strange, but this ground state potential is some kind of rotational, discrete rotational symmetry. Adding this term respect the symmetry. So respect both the asymptotic at 0, at infinity, and the symmetry. And they prove that given such a potential, the spectral determinant satisfies the Bethe equation for quantum KdV if the monodromy about all the poles that you're adding, which are Fuchsian singularities, have trivial monodromy. Okay, so you add a lot of singularities, but they have trivial monodromy. And they also prove that the trivial monodromy condition is equivalent to the following system of algebraic equation for the roots of the polynomial R. Okay, this in the generic case when you assume that the roots, this polynomial R has n roots, and you assume that that are all distinct. Okay, so now now also here in this case of this monster potential, we have this integer big N, and we should prove that there are exactly partition of n solution of this equation. Okay, because we want to find a bijection between Bethe equation, solution of the Bethe equation associated to the number big N, or to a partition with solution of this system, because solution of this system gives us a solution of the Bethe equation. And the important fact here comes from a beautiful mathematical object, which is deceptively simple to write but difficult to analyze, which is something that, I don't know if the name is correct, but called rational extension of the harmonic oscillator. So I just consider this potential, the harmonic oscillator minus twice the second logarithmic derivative of a polynomial u, where u is a polynomial of degree n, such that the monodromy about all the additional singularities are trivial for every value of the energy. Now, it is quite easy to show that you can find solution of this problem. I mean, you can find polynomial u by taking Wronskians of some object. But the problem was, are all solutions obtained by taking Wronskian? The answer is yes. Oblomkov in 1999 proved the following fact, is that the solution, I mean, the monodromy of these, all the monodromy are trivial if and only if u is the Wronskian of a bunch of Hermite polynomials. These H are Hermite polynomials. So to define a Wronskian, you take a partition, and then you take the Wronskian of the Hermite polynomial with these indices. And so in this case of the rational extension of harmonic oscillator, these are classified by partition. Okay, if we take u to be of degree n, the number of rational extensions are really the partition, is the partition of n. And what Riccardo and I prove is that if you take the BLZ, the monster potential, and you do a multi-scale limit, when the momentum is very large, then this monster potential converge to rational extension of the harmonic oscillator. So again, we were able to find partition of integers, solution of BLZ system. Okay, so more precisely, our result is the following. So we assume that there exists a sequence of monster potential, it means of these polynomials, R of L. L is the angular momentum, when L is going to infinity. And then we take, we study the roots of this polynomial R, which are the solution of the BLZ system. And it has the following asymptotic. So the root zk is equal to L squared over alpha plus a constant times L to the 3 alpha times the kth root of the Wronskian of the Hermite polynomial associated to a partition lambda. Okay, so at this moment, we still don't know whether the BLZ system has a solution. But we know that if a solution exists, then it must have this asymptotic for some lambda. So the next problem would be for every lambda to find the family of solution with this asymptotic. But before that, we also proved that if such a solution exists, so given these asymptotics for the roots of the BLZ system, we could compute the asymptotic of the spectrum in the large momentum limit. And so we could prove that if such a solution exists, then the spectral determinant associated to the partition lambda really coincide with the unique solution of the Bethe equation which we had proven to exist, associated to the same partition up to, well, some norming constant, which are here. Okay, as I told you, so we still don't know whether this solution exists, but I mean, of course they exist, but the proof is complicated. The proof is complicated. It is complicated to prove that really a solution of this strange algebraic system of equations written by Bazhanov, Lukyanov, Zamolodhchikov, which such an asymptotic exists. The problem is that this polynomial here can have multiple roots. And when there are multiple roots, well, the perturbation analysis is a nightmare. So with Ricardo, we analyzed the case when three roots coalesce. It's already 20 pages computation. It's in the appendix. Of course, nobody would ever can read it. But we don't have like a general way of constructing it, not yet. But even when there are no multiple roots, so what you have to do when you do perturbation theory, normally you have to invert the Jacobian. So you compute the Jacobian, and you Jacobian of the equation, and then you want to know that some matrix is invertible, essentially, when you do this kind of perturbation analysis. And this, again, technical, but quite funny. So if you construct this matrix, so to every partition you associate a matrix, which is made out of the roots of the Wronskian over Hermite polynomial associated to the partition. So Ricardo and I proved, well, we found an explicit formula for the eigenvalues of this matrix. Explicit, but we found, but it is unproven. We don't know how to prove it. But our formula, which is very like you find in the paper, we give an algorithm to compute this. And then Claire Dunning noticed that our formula is actually, so the spectrum is made of the square of the hooks of the partition. So you have a partition of n, and you have n hooks. You take the square, and these are the eigenvalue of this strange matrix. So we don't know why. There is this paper of 79 by Calogero and collaborators, when they actually prove this formula for the case of the standard Hermite polynomials. But so we don't have any clue for the moment how to generalize. I mean, this approach do not easily generalize to the general case. Okay, so I'm coming to the conclusion. So we have this ODM conjecture for quantum KdV was discovered by Dorey and Tateo, and then was extended by Bazhanov, Lukyanov, and Zamolodhchikov. And we were able to do some analysis on that, and essentially up to a lot of technicalities to prove that it is actually true. I mean, to have the solution of the quantum KdV Bethe equation, we can associate a spectral determinant. So every solution can be written as a spectral determinant. But naturally, we have like a big ODM correspondence, is that in the literature, there are like tens or hundreds of ODM correspondences. Essentially, the idea is that if you have an integrable quantum field theory, integrable by the Bethe equation, then for every state, you have a solution of the Bethe equation, and this should be possible to write that solution as spectral determinant of some differential operator. Okay? So this would say that the Bethe roots for a quantum field theory are the eigenvalues of a differential operator.
Of what order? Could be any order.
Well, we have some guess about that, of course. It is like, let's say, the Hilbert-Polya conjecture for the Bethe equation. But here things are much simpler because we have an infinite set of identities, so the spectral is much more regular. Like, together with Andrea Raimondo and also Daniele Valeri, we have worked, for example, on a higher order case after a paper of Boris Feikin and Edward Franklin. So quantum KdV can be thought as like to be associated to the affinization of SL2 algebra. So for every affine Kac-Moody algebra, you can define, in principle, a quantum KdV model. And so the Bethe states of that generalized quantum KdV model should correspond to some operators. It turns out that these operators are opers, which are more or less scalar or these, on C star, which takes value in the Lagrange dual of that Kac-Moody algebra. And also, we haven't yet analyzed the Destri-de equation, but for example, in Claire's thesis, these are written, I mean, they are known, the Destri-de equation for this kind of models, at least for the simply less case. So it is something that, so our approach could be generalized to that more difficult theories, even though technically it becomes extremely complicated. Okay, so to finish, open questions. So what I think is that this ODM correspondence for quantum KdV is just, it's a tiny piece of an enormous field of research, of which I know very little. So for example, so what is, how do we guess the ODE associated to an integrable quantum field theory? Well, who knows, and why it exists? I mean, is there a theory? Some shouldn't be a mathematical theory, but just an explanation. I mean, first principle explanation is something like that should happen. And even if you exit a little bit from the realm of the ODM correspondences, so there is this fact that this, what I call nonlinear Stokes phenomenon is extremely relevant. I mean, why it is so important? Now there is a problem which is purely, let's say, mine, is that every time I open the archive, there is a new ODM correspondence. Normally, like these are like 150 pages long paper, and I mean, I lost track of all the ODM correspondence. I would like to prove them, but I don't even know how to keep track of all these new discoveries. So having a theory beyond that would be, I mean, is extremely important. Okay, thank you very much.
Questions for Davide?
Yes, just on this slide. Inversely, does every, say, Schrödinger equation with a polynomial potential, not homogeneous, does it correspond to an integrable model?
Yeah, it's not really my area of expertise, but yes, I think so. I mean, I'm currently working with Evgeny Mukin and Andrea Raimondo. There is a paper by Gayot collaborators of a few months ago, and they consider some, not really, but they associate more or less to a polynomial there is something like that. But quantum KdV, it's like a bit in a very, it's kind of a strange limit. There is this family, bigger family of ODEs and quantum field theory that should be associated, and quantum KdV is a very strange limit of that family, but yeah, I'm not an expert, but probably yes. Even though the theorem would look like quite different from quantum KdV because it is a very special limit.
Other questions? I'll go first.
Thank you. So I also struggle to keep track of all of these ODE-IM correspondences. Do you have any clues as to what should be going on if we have a superalgebra?
Well, we actually tried to work this out. Well, the fact is that it seems that it is possible to write these these OPERs when the superalgebras has a presentation just in terms of fermionic roots. Okay, so these are particular. So there are fermionic roots, bosonic roots, but there are like a fermionic reflection which exchanges a bosonic root to a fermionic root. And when there exists a presentation of the algebra which is made purely of fermionic roots, then it is possible. It seems so, but then the ODE split, and it's nothing interesting. Yeah, you get several copies of, let's say, of bosonic ODEs. That's what I try to work it out, but yeah, nothing too exciting so far on that part.
Could you go back to the slide about the Wiener-Hopf kernel, please? Yeah. I just want to understand this claim. So that WKB representation is from the linearized
Yes.
case. So when you iterate in the integral equation, does it match iteration of higher order WKB term by term? Is that what you're saying?
When I iterate this, I don't get I get something converging. It's not the same.
Okay.
It's not the same as. You could expand. You could expand this in P and get higher order WKB correction. But when you iterate, you are not expanding because you're getting something which converge actually quite fast.
Okay. But the expansion in P would match the WKB expansion.
For the spectrum, yeah. Because I haven't tried it just because it's a consequence of the fact that it gives you the exact.
Okay. All right, thanks.
I have a remark possibly related to your question, actually. I iterate a fixed point problem to get the spectrum. Very curiously, the iteration is the identity on the asymptotic coefficients. So there is some non-uniformity, very strange non-uniformity. The iteration converges better and better, but it doesn't produce the higher order WKB coefficients from the leading one.
Yeah, because the iteration converges while WKB does not converge. So, but you can, in principle, you write the WKB expansion and you put it in this equation, and if you're good enough, you should be able to obtain all these terms.
Any final question?
Maybe one more.
Go for it.
One more remark, as I said at lunchtime perhaps, but in all this picture, the Borel plane has disappeared. Can you restore it somehow? Can you reinterpret these, all these formalism in the Borel plane?
But I really don't know, because when we started work on it and we were following what Bazhanov, Lukyanov, Zamolodhchikov did, so of course we took the Mellin transform, so I don't know whether it is Borel plane or not. And that's why you get these formulas. But then we soon realized that it was not good to do analysis, so it was not a good setting to do analysis. So we went to a purely real stuff, let's say. Yeah, because we have this, so this is something like in real analysis. But originally, the Bestrovec equation, it was never written like that in the literature. It was like a contour integral in the complex plane, which is more like that setting. But it was impossible to do analysis in that setting, and impossible to do analysis in the Mellin plane, because so all these objects are barely, the Mellin transform is barely convergent. So you don't have enough derivative to be able to do things. So it was technically very difficult to invert. I mean, all this problem of inverting the Mellin transform was becoming crazy. So we just dropped all the Mellin plane and just focus on the real plane.
Okay, then, well, let's thank Davide for his seminar.
Thank you.
And everyone can enjoy their afternoon.